Hey everyone, my name is Atharva and I'm from Trinity College Dublin. In this tutorial, we'll be taking a look at how you can add your signature algorithms into the XRP Ledger. So, we would follow 7 steps in order to do this. I've named them climate. So, first one is compatibility. So, in compatibility, you need to check if your algorithm fits XRPL. We assess if your signing algorithm meets XRPL security and performance requirements. We ensure the algorithm is implemented in a language and style which is compatible with the XRPL's C++ code base. We also check for the existing dependencies or conflicts with the XRPL's cryptographic modules. So here I have Crystals-Dilithium opened up, and we would be comparing if our dilithium has the functions which are compatible with the XRPL's current code base. So we have a function which generates the public key and private key. We have a function which computes the signature. We have a function which computes the signed message. We have a function which verifies the signature. We have a function which verifies the signed message. Now we take a look if the language is compatible with the XRPL. Since we could see from here, dilithium contains CMakeLists, which is also something which XRPL contains, along with the Conan file for linking the libraries. We just call Crystals-Dilithium, we point our CMakeList to the one in the dilithium. With that, we finish the first step, which is we check if our algorithm is compatible with XRP Ledger. Now, let's move on to step number 2, layout analysis. In this step, we analyze the cryptographic functions within the XRPL. We review XRPL's cryptographic architecture, which contains key management, signing, verification, and so on. We identify all the cryptographic functions, for example, generate key pair, sign, verify, and so on. And this is something which your algorithm must support. We map our algorithm's primitives to XRPL's expected interfaces and data flow. All right, so I have opened up XRPL's GitHub repo, and we are in a file called secretkey.cpp, which essentially contains all the cryptographic functions required for various operations. So we have a function called sign digest. We have a function called sign. We have a function called random secret key, generate secret key. We have a function called derive public key. We have a function called generate key pair. We have a function called random key pair. Now, so we have finished first 2 sub-steps of the layout analysis. We identified all the cryptographic functions. We reviewed XRPL's cryptographic architecture. Now it's time to map your algorithm's primitives to the XRPL. Alright, so we are just comparing the equivalent functions used in dilithium versus XRPL. We have a function which generates a public key and a private key. We have a function called cryptokeyPairSeed, which essentially generates a public key and a private key using a seed. We have a function which computes the signature. We have a function which computes the signed message. We have a function which verifies the signature. And lastly, we have a function which verifies the signed message. That completes our second step of layout analysis. Now it's time for step 3, which is integration. In integration, our main goal is to link our algorithm into the CMakeLists and Conan file. So it's divided into 3 more steps. We add our algorithm's source files to XRPL's CMakeLists and Conan file for proper build and dependency management. We ensure all required libraries are available and correctly linked, and then we test the build process to confirm that our algorithm compiles and links without giving us any errors. So here I have CMakeLists, which I've already integrated Dilithium with, and we'll just take a look at that in order to understand how you can link your algorithm in the CMakeLists of XRPL. So first of all, we include our algorithms library. We define the path to our API header file, which points out to all the cryptographic functions required in the XRPL. So here we link all the libraries to the target link libraries command, and we include our algorithms target within the function. Now we are in the Conan file, and here there's just one small change. We just include the name of our library, which we are including in the CMakeList. So that would be included in the package. So we have finished point 1 and point 2 in the integration steps. Now let's just test our build process to confirm that our algorithm combines and links without the errors. So here I have already built my version of integrated Crystals-Dilithium in the XRPL. So we would just make it again to save time, because we don't want to wait 40 minutes right now just for the sake of verification of the library. So as you can see, it built Dilithium 2, it also built FIPS 202, and it also built the test for Dilithium 2, and it built without giving us errors. This proves the point that that Dilithium has been integrated in the current XRPL's directory. With this, we now come to the 4th step, which is make KeyType. Here we introduce our algorithm as a new KeyType. So it again has 3 steps. We register our algorithm as a new KeyType in the XRPL's KeyType header file. Now we are in the KeyType header file. As you can see, I have added Dilithium as another value in the enum class KeyType. So we have to register our algorithm as a new KeyType in the XRPL's KeyType header file. This comes in by assigning a unique identifier, let's say KeyType Dilithium, and update relevant enums and type checks. So here I'm in the XRPL's KeyType header file, and as you can see, we have added Dilithium as another value within the enum class KeyType. We have also changed some relevant functions as well by adding new value of Dilithium alongside. Now we come to the step 3, which is implement type detection and routing logic so XRPL can recognize and use your new KeyType. So here we have 2 functions. One is called KeyType from string, another one is toString. So we have added Dilithium as a 3rd value alongside SECP and ED25519. This completes step 4, and now we proceed to the next step, which is adjust key size. Here we modify our key size array and constants to include our algorithm's public and private key sizes. Since your algorithm's key sizes would be different, it is recommended to convert the static key size array into a dynamic size buffer. Right, so here we are back in the secret key .cpp, and we have changed the constructor with an additional key type. So it would not just take 32, which is the size for SCCP. Now it also checks for the key size 2528, which is the size of dilithium. You can replace this with your algorithm's key size, and then that should be good to go. With that said, let's come to the third point, which is we test the edge cases to prevent buffer overflows or truncations. You can do this step once you have modified your cryptographic functions, which we would be doing in the next step. With that said, we come to the second last step, which is we tweak the crypto functions to include your algorithm. We extend or modify the cryptographic functions like sign, verify, derive public key, generate secret key, etc. To include your cryptographic. So here we extend or modify the cryptographic functions like sign, verify, derive public key, etc. to include the additional new key type. Alright, we are back in the secret key.cpp. Let's take the function generate secret key for the example of the time being. Previously, there were only type ET25519 with its respective logic for processing, and type SCCP256K1 along with its processing logic. Now we have added one more type, dilithium, which has its own processing logic. So when a generate secret key function would be called, and if the argument is passed as dilithium in the parameter key type, it would execute the logic which is mentioned here. So the second point is ensure your algorithm is included in all relevant switch case statements and function overloads. What this means is in the function public key, we have two parameters, which is the key type and the secret key. What this means is for the key type SCCP and ET25519, it can derive the public key from the secret key. Since this is not so straightforward in dilithium, we have to use another parameter called seed, and then we use the logic to generate the public, we generate a key pair, and then we destroy the secret key. So in the end, we just have the public key. Hence, we satisfy the logic of deriving a public key in a deterministic process. Point 3, which is very crucial, is we should maintain a backward compatibility with existing algorithms like SCCP and ET25519. Let's take a different function, for example, this time a random key pair. What this means is we cannot just strike off SCCP and ET25519. We need to keep them alongside dilithium, so user can still use SCCP or ET25519 if they want to. With this, we finally come to the last step, which is evaluate test. In this step, we add or update the test cases for key generation, signing, verification, and transaction processing using our algorithm alongside existing algorithms. We compare outputs and error handling with existing algorithms to ensure consistency, and then we run the full XRPL test suite to validate integration and catch regressions. So I am in a test file STTX. For example, here we have a test called test object. So we are in the STTX test file, and here we can see that we have a test called test malformed serialized form, which right now is using key type SCCP. One way to test your algorithm is we would clone the test case as it is, and we then just modify the key type to your algorithms. So all the existing test logic would remain intact and you would get the result using your algorithm. Now we are back to the same test case, but this time as you can see, we have cloned the SCTX and I've replaced and named it SCTX-Dilithium, so it would not clash with the same name in the test case and would not result in an error. Like I said before, we have kept everything, all the logic exactly the same, but we have just changed the name of the test case and key type to dilithium. With that, we come to the last step, which is run the full XRPL test suite to validate integration and catch regressions. I'll just do one more point before we run the full test suite. So now we have tested the existing logic with the dilithium. If you want, you can add your own test cases to verify or check some additional results which are not included in the current test. For example, I have created a new test suite called secret key functions. What this does is this basically performs different operations using different key types, so we could compare the performances of all the three algorithms and it gives us a transparent comparison. So now I have typed in the command to execute this particular test suite, and if we just press enter, hopefully if all your algorithm is like tightly integrated with the existing functions, it should run and give us 0 errors. Like I said, we tested 10 cases, we tested 3 tests in total, and we ended up with 0 failures. This proves the point that your algorithm has now been successfully integrated within your system's XRPL. Now from here on, you are good to run the full test suite and see and compare the results by running the same suite but not using your algorithms. With that said, we come to end of this tutorial. Thank you very much for tuning in, and keep on coding, keep on building new stuff, and I'll see you guys soon.